The oscillating current in the secondary may continue for some time. The current from the supply transformer begins charging the capacitor C1 again and the cycle repeats. This entire cycle takes place very rapidly, the oscillations dying out in a time of the order of a millisecond. Each spark across the spark gap produces a pulse of damped sinusoidal high voltage at the output terminal of the coil. Each pulse dies out before the next spark occurs, so the coil generates a string of damped waves, not a continuous sinusoidal voltage. 9. The high voltage from the supply transformer that charges capacitor is a 50 or 60 Hz sine wave. Depending on how the spark gap is set, usually 1 or 2 sparks occur at the peak of each half cycle of the mains current, so there are more than 100 sparks per second. Thus the spark at the spark gap appears continuous, as do the high voltage streamers from the top of the coil. The supply transformer, T, secondary winding is connected across the primary tuned circuit. It might seem that the transformer would be a leakage path for the RF current, damping the oscillations. However, its large inductance gives it a very high impedance at the resonant frequency, so it acts as an open circuit to the oscillating current. If the supply transformer has inadequate short circuit inductance, radio frequency kicks are placed in its secondary leads to block the RF current. Oscillation frequency. To produce the largest output voltage, the primary and secondary tuned circuits are adjusted to resonance with each other. 8, 9, 12. The resonant frequencies of the primary and secondary circuits, and, are determined by the inductance and capacitance in each circuit. 8, 9, 12. Generally the secondary is not adjustable, so the primary circuit is tuned, usually by a movable tap on the primary coil L1, until it resonates at the same frequency as the secondary. Thus the condition for resonance between primary and secondary is the resonant frequency of Tesla coils is in the low radio frequency, RF, range, usually between 50 Kz and 1 MHz. However, because of the impulsive nature of the spark, they produce broadband radio noise and without shielding can be a significant source of RFI, interfering with nearby radio and television reception. Output voltage. Large coil producing 3.5 meter, 10-foot, streamer arcs indicating a potential of millions of volts in a resonant transformer. The high voltage is produced by resonance. The output voltage is not proportional to the turns ratio, as in an ordinary transformer. 14, 19. It can be calculated approximately from conservation of energy. At the beginning of the cycle, when the spark starts, all of the energy in the primary circuit is stored in the primary capacitor. If is the voltage at which the spark gap breaks down, which is usually close to the peak output voltage of the supply transformer T. This energy is during the ring up. This energy is transferred to the secondary circuit. Although some is lost as sheet in the spark and other resistances, in modern coils, over 85% of the energy ends up in the secondary. 9. At the peak of the secondary sinusoidal voltage waveform, all the energy in the secondary is stored in the capacitance between the ends of the secondary coil, assuming no energy losses. Substituting into this equation and simplifying, the peak secondary voltage is 8, 9, 14. The second formula above is derived from the first using the resonance condition. 14. Since the capacitance of the secondary coil is very small compared to the primary capacitor, the primary voltage is stepped up to a high value. 9. The above peak voltage is only achieved in coils in which air discharges do not occur. In coils which produce sparks, like entertainment coils, the peak voltage on the terminal is limited to the voltage at which air breaks down and becomes conductive. 9, 14, 16. As the output voltage increases during each voltage pulse, it reaches the point where the air next to the high voltage terminal ionizes and corona, brush, discharges, and streamer arcs break out from the terminal. This happens when the electric field strength exceeds the dielectric strength of the air, about 30 kV per centimeter. Since the electric field is greatest at sharp points and edges, air discharges start at these points on the high voltage terminal. The voltage on the high voltage terminal cannot increase above the air breakdown voltage, because additional electric charge pumped into the terminal from the secondary winding just escapes into the air. The output voltage of open-air Tesla coils is limited to a few million volts by air breakdown, 5, but higher voltages can be achieved by coils immersed in pressurized tanks of insulating oil. Top-load or toroid electrode. Solid-state DRSSTC Tesla coil with pointed wire attached to toroid tar produce brush discharge. Most Tesla coil designs have a smooth spherical or toroidal shaped metal electrode on the high voltage terminal. The electrode serves one plate of a capacitor, with the earth as the other plate, forming the tuned circuit with the secondary winding. Although the toroid increases the secondary capacitance, which tends to reduce peak voltage, its main effect is that its large diameter curved surface reduces the potential gradient, electric field, at the high voltage terminal. It functions similarly to a corona ring, increasing the voltage threshold at which air discharges such as corona and brush discharges occur. 20. Suppressing premature air breakdown and energy loss allows the voltage to build to higher values on the peaks of the waveform, creating longer, more spectacular streamers when air discharges finally occur. 14. If the top electrode is large and smooth enough, the electric field at its surface may never get high enough even at the peak voltage to cause air breakdown, and air discharge will not occur. Some entertainment coils have a sharp spark point projecting from the torus to star discharges. 20. Types. The term Tesla coil is applied to a number of high-voltage resonant transformer circuits. Excitation. Tesla coil circuits can be classified by the type of excitation they use. What type of circuit is used to apply current to the primary winding of the resonant transformer? Sad smiley 5. 21. 22. Spark excited or spark gap Tesla coil. SGTC. This type uses a spark gap to close the primary circuit, exciting oscillations in the resonant transformer. Spark gaps have disadvantages due to the high primary currents they must handle. They produce a very loud noise while operating, noxious ozone gas, and high temperatures which may require a cooling system. The energy dissipated in the spark also reduces the Q factor and the output voltage. Tesla's coils were all spark excited. Static spark gap. This is the most common type, which was described in detail in the previous section. It is used in most entertainment coils. An AC voltage from a high voltage supply transformer charges a capacitor, which discharges through the spark gap. The spark rate is not adjustable but is determined by the 50 or 60 Hz line frequency. Multiple sparks may occur on each half cycle, so the pulses of output voltage may not be equally spaced. Static triggered spark gap. Commercial and industrial circuits often apply a DC voltage from a power supply to charge the capacitor, and use high voltage pulses generated by an oscillator applied to a triggering electrode to trigger the spark. 6. 22. This allows control of the spark rate and exciting voltage. Commercial spark gaps are often enclosed in an insulating gas atmosphere such as sulfur hexafluoride, reducing the length and thus the energy loss in the spark. Rotary spark gap. These use a spark gap consisting of electrodes around the periphery of a wheel rotated at high speed by a motor, which create sparks when they pass by a stationary electrode. 22. Tesla used this type on his big coils, and they are used today on large entertainment coils. The rapid separation speed of the electrodes quenches a spark quickly, allowing first notch quenching, making possible higher voltages. Fuel is usually driven by a synchronous motor, so the sparks are synchronized with the AC line frequency, the spark occurring at the same point on the AC waveform on each cycle, so the primary pulses are repeatable. Switched or solid-state Tesla coil, SSTC. These use power semiconductor devices, usually thyristors or transistors such as MOSFETs or IGBTs. 6. Triggered by a solid-state oscillator circuit to switch pulses of voltage from a DC power supply through the primary winding. 22. They provide pulsed excitation without the disadvantages of a spark gap, the loud noise, high temperatures, and poor efficiency. The voltage, frequency, and excitation waveform can be finely controllable. SSDCs are used in most commercial, industrial, and research applications. 6. As well as higher quality entertainment coils. Single resonant solid state Tesla coil, SRSSTC. In this circuit the primary does not have a resonant capacitor and so is not a double-tuned circuit. Only the secondary is. The current to the primary from the switching transistors excites resonance in the secondary tuned circuit. Single-tuned SSDCs are simpler, but the resonant circuit has their total Q factor depends only on the secondary side resonant. Dual resonant solid-state Tesla coil, DRSSTC. The circuit is similar to the double-tuned spark-excited circuit, except in place of the AC supply transformer, T, in the primary circuit a DC power supply charges the capacitor, and in place of the spark gap semiconductor switches complete the circuit between the capacitor and the primary coil. Singing Tesla coil or musical Tesla coil. This is not a separate type of excitation, but a modification to the solid-state primary circuit to create a Tesla coil which can be played like a musical instrument, with its high-voltage discharges reproducing simple musical tones. The drive voltage pulses applied to the primary are modulated at an audio rate by a solid-state interrupter circuit, causing the arc discharge from the high-voltage terminal to emit sounds. Only tones and simple chords have been produced so far. The coil cannot function as a loudspeaker, reproducing complex music or voice sounds. The sound output is controlled by a keyboard or MIDI file applied to the circuit through a MIDI interface. Two modulation techniques have been used, amplitude modulation of peak sitting voltage, and PFM, pulse frequency modulation. These are mainly built as novelties for entertainment. Continuous wave. In these the transformer is driven by a feedback oscillator, which applies a pulse of current to the primary winding each cycle of the RF current, exciting a continuous oscillation. 22. The primary tuned circuit serves as the tank circuit of the oscillator, and the circuit resembles a radio transmitter. Unlike the previous circuits which generate a pulsed output, they generate a continuous sine wave output. Power vacuum tubes are often used as active devices instead of transistors because they are more robust and tolerant of overloads. In general, continuous excitation produces lower output voltages from a given input power tone pulsed excitation. 22. Number of coils. Tesla circuits can also be classified by how many resonant coils, inductors, they contain. SAD Smiley 23, 24, 2-coil or double resonant circuits. Virtually all present Tesla coils use the 2-coil resonant transformer, consisting of a primary winding to which current pulses are applied and a secondary winding that produces the high voltage, invented by Tesla in 1891. The term Tesla coil normally refers to these circuits. 3-coil, triple resonant, or magnifier circuits. These are circuits with 3 coils, based on Tesla's magnifying transmitter circuit which he began experimenting with sometime before 1898 and installed in his Colorado Springs lab 1899-1900, and patented in 1902. 25, 26, 27. They consist of a 2-coil Ecore step-up transformer similar to the Tesla transformer, with the secondary connected to a third coil not magnetically coupled to the others, called the extra or resonator coil, which is series-fed and resonates with its own capacitance. The output is taken from the free end of this coil. The presence of 3 energy-storing tank circuits gives this circuit more complicated resonant behavior. 28. It is the subject of research, but has been used in few practical applications. History. Henry Rowland's 1889